Hi everyone, in this new tutorial I will show you a summary of the chapter E about compression of the Aisc code in order to understand the main concepts, and also I would like to do a revision of every formula to give you the chance to understand the main concept behind them. Okay, let's start. First of all, I separate the verifications in the chapter E for members without elements, slender elements, and for members with slender elements. As you can see, both types of members has almost the same verifications. We have flexural buckling, torsional buckling, and flexural-torsional buckling for the first case. And in the second case, we have the same plus the local buckling in the chapter E7. So what's the main difference here is that for slender elements, we have to check if they will have local buckling. The other limit states applies for a global behavior of the column or the element. If we want to see how this limit states looks like, here are some pictures. The first case is the flexural buckling from the chapter E3, and as you can see, it's represented by distortion or a displacement of the cross section in a lateral form. It can be in the main or the major axis or the minor axis. Secondly, we have torsional buckling, which is represented by a rotation of the cross section in the center axis. And then we have the flexural-torsional buckling, which is a combination from the previous ones, and as you can see, applies mainly for members with singly symmetry. There is a displacement of the cross section and also a rotation of that. And in the fourth case, this is a local buckling. You can see a deformation of the wings or of the flanges of this column. That its local buckling does not apply for the entire element, only in a local way. Okay, now we will review each of the equations that applies for each of one, and we will try to understand the concept behind them. First of all, I would like to review the global buckling, and the main factor that affects its behavior is effective length. And as you can see, effective length depends on the type of fixation that this column has. You can see that, for example, a double pinned column has a full length, but if you have a double fixed, you will have a reduced effective length due to the change in the curvature of the deformation. Okay, you have to apply the respective effective length factor to your design in order to do a proper verification of the design. Then we have the local buckling, and local buckling, you can find these equations or these limits in the table B4.1a of the code in stability chapter. Okay, there is not too much to review here, just the slenderness limit. Also, this code gives you this table for without the slender elements and with slender elements, and as you can see, the difference here is that this table, this last column, contains LB, which is local buckling. That's the only difference, because all the other limit states are the same. You can see flexural buckling, torsional buckling, flexural-torsional, flexural-torsional, but you can see that here is local buckling as an additional. As I mentioned, it's a combination between these two. Let's start with the equations. First of all, we have a flexural buckling, which is the chapter E3, and as you can see, there is two equations here to be applied that will depend on the value of the slenderness, of the global slenderness of this member. The slenderness is considered as the length divided by the radius of gyration of the cross section, right? Now, why are two equations? If we review first of all the Euler equation for buckling, is this dashed curve, but if we compare the real test doing for columns, real columns, you can see that in this step it's very good approximation of the real test, the curve, but there is a limit here. The columns does not being represented by the curve in this part of the slenderness. So the main reason for that is that in this zone you will have a plastic behavior, which is influenced due to the yield stress. That's why the real behavior is not the dashed curve, is this curve which is here, and as you can see an elastic behavior here and also a plastic behavior here. So what it's doing, the code, it's using two equations for the representation of these two behaviors. If we look this picture, you can see that both equations are considered to take in account both behaviors, and the limit of slenderness is this value here, which represents the pass from the elastic through the plastic behavior. That is the reason of the code are using two equations. Okay, I hope it's clear. The second chapter is E4, which represents the torsional buckling. And for torsional buckling, we have the same equation, general equation, but we have this detailed equation here. And the difference here is that you have two components. Also, you have an adjustment value, which is related to the flexural behavior of the member. But the most important components here are these ones. As you can see, torsion is a composed behavior. One of them is the pure torsion and the other one is the warping torsion. So this equation is trying to represent that both behaviors. The first one is the warping behavior, that's why it contains the warping constant, and the second one is related to the pure torsion behavior. That's why it contains the torsion constant and the shear center. Okay, you can see in this picture both behaviors that composed the total torsion behavior, and that is why this equation has this form. Then we have the flexural-torsional buckling, which is a combination from the previous two behaviors, and as you can see, it's a very long equation, but it's more easy than we can think. The first member, if you review it in detail, is just an average. It's just an average of two values, and then it's multiplied by a factor. If we review which means these factors, the first one is just elastic buckling, the second one is just torsion component, and then we have an interaction factor, which is this whole value here. Is just a curve. It's represented by this curve, which takes values between 0 and 1, and its function is to compensate the distance between these values, because the code use a conservative value for the design, not just the average between these two components. Okay. If we review an example here, for example, if I have for these two values, these ones, 199, I will have an interaction factor of 0.99, which is virtually 1. So if I have these two values, I will have as a final result just the average, right? But if I have these two values, for example, 80 megapascals and 40 megapascals, first of all, I have to take the average, which is 60, and then I will have an interaction factor of 0.66. So the average, 0.6, I will multiply it for this interaction factor. So the final value are going to be close to 40 in order to be conservative. And that's why this equation has this form. Okay, it's not too difficult. I think it's a very conceptual way to understand the flexural-torsional buckling. And finally, we have the local buckling in the section E7, and in this case you will have also a limit, a slenderness limit, which will give us an idea that only elements over some limits are going to be subject to local buckling, not all the elements, only these ones. And these equations represent just a reduction factor for the original width of the element, for example the width of the flange, multiplied by a reduction factor in order to consider the a more conservative way to review this kind of slender element for the local buckling. Okay, so it's not a complex equation. That's the main reason of its form. Finally, I would like to show you again this picture. I think it summarizes the main elements to be considered, and I hope you can understand each of the limit states. My idea is to share with you another tutorials showing the different limit states for the other behaviors or the other loads for as flexure, torsion, and tension, and also shear. So stay tuned for future tutorials, and see you later. Bye bye.